Hi everybody. I'm going to talk about exponential growth and decay today, and we're going to come up with kind of the big picture of what this is, why it's kind of important. And I'm going to start off with an example of exponential growth and how we're going to model this using mathematics, but we want to see what we're modeling, what situation actually is happening. Let's say that you have a cell in your body, one cell, there it is. And let's say every 20 minutes that cell divides. So when that cell divides, what's going to happen is it's going to break up into two cells. Now 20 minutes later, so this is at 0 minutes. And it's important that you have your first situation at 0 minutes. Then you have at 20 minutes, you got your two cells. Now, from here, that cell divides after 20 more minutes. This cell divides into two, and that's at the 40-minute mark. So after 40 minutes, one cell has divided into four cells. After 60 minutes, 1 hour, these cells have divided after 80 minutes. These cells have divided and we've gone from 1 to 2 to 4 to 8 to 16. Now hopefully you're starting to see a pattern here. And it's starting to get difficult to draw, but after 100 minutes, we will end up with 32 cells. After 120 minutes, 2 hours, we're going to end up with 64. And then we keep going and going and going. So the idea of exponential growth is this idea right here, that you start with 1 and it doubles. And then you have 2 of them. Then those double. Because from here, what we have is 1 times 1. Then you get 1 times 2, because it doubles in here. So our total is 1. Now here our total is 2, like we had there. Now we're going to take that total, 2, and we're going to double that, and you get to 4. Then we're going to take that 4, you double that, and we get to 8. Then you take 8, and you double that, and you get to 16. You get to 16, you double that, you get to 32. The next step, 32 times 2, you get to 64. Now, one of the interesting things that we're going to do is we're going to say that this is, we'll just call them steps for right now. That's step 0. Step 0, kind of like patient 0 in those movies where people get sick. Everything has to start somewhere. Any type of growth has to start from one single place. And we call the starting point the 0 step. Because you got to start with something. In this case, we started with 1. And now, we have to take a look at what is the pattern. What are we doing to each step? Well, we're taking that starting amount. And in this case, you take the starting amount, which is 1. So and we're multiplying it by 2. Now, let me ask you this. The starting amount. How does that relate back to here? Well, this 2 is equal to this 2, which is equal to this starting amount times 2. So what we can do is actually say, this is the starting amount times 2 times another 2. And what we get is the starting amount, which I'll call big capital S right now, times 2 squared. Up here it was the starting amount times 2 to the first power. Now, I'll say that was step 0. So this is step 0. I'll put my steps over here. And every time we go through a division, every 20 minutes, if the cell is dividing, that's a new step. So that's step 1. That's step 2. That's step 3. That's step 4. That's step 5. Step 6. And it'll continue on and on and on. Now, the end result, the 4 here, was the starting amount S times 2 squared. So the 4 here is that same value, which is right there. So this is going to be the starting amount times 2 squared. Then we have to double it again. So now we have S times 2 to the third power. Now, let's take a look if we can see a pattern. For the first one, for step 0, I actually only have 1. And that's just S. So that's our starting point, that's our starting amount. That's the amount that I had. And then I use that starting amount times 2, 2 to the first power. Starting amount times 2, that's 2 squared. Now I get 2 cubed in step 3. What do you think I'm going to get in step 4? The starting amount times 2 to what power? Well, in step 1 was to the first power. Step 2 was to the second power. Step 3 was to the third power. Step 4 would be to the fourth power. In step 5, it's going to be the starting amount times 2 to the fifth power. Step 6, starting amount times 2 to the sixth power. And so on and so on. If I'm in step, so I want to be in step 100, I can take the starting amount, which is S, times 2 to the step number, which is 100. And that's going to tell me how many cells that I have after the first cell started the chain reaction of cells dividing. And so we can start with that. Now, this is exponential growth and it's exponential decay, because we could easily have gone from 32 to 16, 16 to 8, 8 to 4, 4 to 2, 2 to 1, and from there on. We can generalize the equation by saying, let's say f of x is equal to the starting amount times 1 plus the rate of growth to the x power, where the starting amount, that's what it is. So f of x is going to be the amount after x steps. The starting amount, well, that's exactly what it sounds like. It's the starting amount. X is equal to the number of steps. Just like here, I wanted step 100. So after 100 cell divisions, I just take 2 to the 100. Now, this idea 1 plus the rate, whatever the growth or decay rate is, what this really means is 100%. You take the whole original amount, and then you're either going to add a growth percentage, or you're going to subtract a decay percentage. Now, for our situation up here with the cells, here's what the equation looks like. F of x is equal to 1 times 1 plus 1 to the x power. So this equals f of x. Well, before I do that, let me tell you this. This is 100%. That's saying I'm going to take 100% of the original, which is what we're going to deal with. And in this case, when it divides, we get 100% return. 1 becomes 2 because I have like the original and 100% new one. So there's your 100%. So if my growth rate is 100%, which is 1.0, remember that's a 1.0, that's a 1.0. If it was like 2%, that would be equal to 0.02. So you'd have 1.02. That's what we're really coming up with in this case. So I get my f of x is equal to 1, which is my original amount, times 2 to the x power. And that says we're actually doubling the original, or doubling the amount in each step. So that's how we deal with and kind of model the situation because of what we're having here. Now, a good decay model is what we call half-life. And let's say you have 32 grams of some type of element that has a half-life of 10 minutes. So every 10 minutes, the amount cuts in half. So let's do this on a number line. At time 0, when we start, we have 32 grams. At 10 minutes, how much do we have? We have 32 times 1/2, which is equal to 16. After 20 minutes, how much do we have? Well, we take half of 16, so we get 16 times 1/2, which is 8. After 30 minutes, we have 8 times 1/2, which is 4. After 40 minutes, 4 times 1/2, which is 2. After 60 minutes, 2 times 1/2, which is equal to 1. After 10, 20, 30, 40, that's after 50 minutes, sorry. 60 minutes. You get 1 times 1/2, which is equal to 1/2. After 70 minutes, you get 1/2 times 1/2. So we take a half of a half, which is equal to 1/4, and so on and so on. What are we multiplying by? We're multiplying by a half every single time. So for a half-life, this is a decay model because we're losing amounts. You'd say f of x is going to be equal, in this case, to the original amount, which was 32 grams, times 1/2, because we're cutting it in half and raising it to the power x. So if we raise it to 0, 1/2 to the 0 power is 1. Anything to the 0 power is 1, and you got the whole thing. So at step 0, we get that. This is step 0. That's step 1, step 2, step 3, step 4, step 5, step 6, step 7. So we can set up this equation, and we know after how many steps we're going to know how much of the material that we have left. So that's what we're going to do the next couple days. So take a look at this. We're just going to, it's a repeat multiplication by the same factor. Things are growing by the same amount. Just like here, things are growing by 200% because you get the original and a new one, a brand new one, a total new one, not a half of a new one, not just a section of a new one. You get the entire thing. So you get 100%. You get a 100% brand new one and the original. And then you'll get, from here, you'll get the original plus 100%, and the original of this one plus 100%. So it's always going to be that 100%. This one is always going to be half. But you can have rates from anywhere from, you don't want 0, but any type of percentage, any type of rate, it's all going to fit into this same formula. F of x is equal to the starting amount times 1 plus the rate to the x power. And this is our function. It's our formula. It's the structure that we're going to be dealing with. So, like I said, we'll be doing some work in class on this stuff, and we will be good to go.